So integral calculus is what this particular section is about. First of all, a little bit of a note on the notation that's involved with it. So mathematically, just like in differential calculus, we use dy by dx to represent the differential, or f prime, this prime notation to represent the differential. In integral calculus, this symbol represents the integral. And in differential calculus, we talk about differentiating something with respect to a variable. So this is called the dependent variable, this is the independent variable. So we have to differentiate with respect to something, x, or with respect to t. Just in the same way, when we integrate with respect to a variable. And so in that case, that's the dx bit here. So I'm integrating 5x squared with respect to x. That's how you read that. It doesn't mean 5x squared times dx. The dx is a notation to tell us what the variable is in this function here, which is x. So again, this reads as I'm going to integrate the function 5x squared with respect to x. Okay? And the answer turns out to be 5x cubed over 3 plus this constant c. So it's like differential calculus. In a lot of cases, we can just write the answer down if we know the rules. The integral can be thought of as the inverse function of the differential function. So if I've differentiated a function and I want to get back to what the original function was, I would integrate it. So you can use integration to get back to the original function, and that's a very big use of integration actually. Later on in the engineering course, if you carry on with the studies, you'll be looking at differential equations. They're just equations that involve differentials, where we know how something's moving and we want to get back to the function that describes that movement. So we solve the differential equation. And lots of the maths that we're looking at the moment is about ways to end up doing that. And integration is obviously involved with that because that gets us back. So that's an introduction to the idea of this integration and what it's used to do. As well as allowing us to get back to the original function or find a function that describes a situation, solve a differential equation in other words. It also allows us to find the area under a curve. So if I've got a speed against time curve here, this first example, and this is how it behaves, if I find the area underneath this curve, then the units of that area are going to be the units of whatever this is multiplied by the units of whatever this is, because it's the area is this length times by this length. And that's speed times time, which is distance if you think about it. If I multiply my speed by how long I've been going at that speed for, 30 miles an hour for an hour, how far have I gone? 30 miles. So this area tells me the distance travelled. So if I want to know the area, the distance travelled, I find the area under a speed time curve. How do I do that? I integrate. Another example, force against distance. We might have talked about the equation for work, which is force times distance. So the area under a force distance curve tells us the work done or the energy used. Very useful when you're considering stressing materials and stuff like that. How do we find the area under the curve? We integrate. So a powerful mathematical tool, this idea of integration. Let's look at this example. When we differentiate this function, y equals 5x to the 4 plus 8. So we've looked at the idea of differentiating a function. Here's a function, y equals 5x to the 4 plus 8. If I differentiate that, bring the 4 down, times it by the 5 in front to get 20, take 1 off the power, 20x cubed. But what's the differential of 8 at constant? 0. So that's disappeared, and when we get the differential, we end up with 20x cubed, and the constant that was there has disappeared. So when I integrate, and we'll look at the rules in a second, when I integrate the differential here, 20x cubed, with respect to x, I get back to the 5x to the 4, but it doesn't tell me what the 8 is, because that's disappeared. So all I can do is say plus c, and then I'm going to need further information to be able to work out what c is. So often that's the case. I need initial conditions, things like that, to be able to work out what c is. So when we integrate, we always add this constant that could have disappeared when we differentiated. Okay. So here is, like common differentials, a table. Here is a table of common integrals. So at some point you might want to take this out of the these notes or copy this out. So you've got, along with your table of differentials and your table of laws of indices, you've got this table of common integrals. So as with the table of common differentials, here is the rule, and the most common rule is this one, so like the first one, okay? Note at the end of each one of the integrals is this plus c all the way down the table. We always add this c at the end. The first rule is telling us, if we look at this first rule, it's the exact opposite of the differential one. Instead of taking one away from the power, we add one to the power, so the power becomes n plus 1. That sort of makes sense if you're going to get back to the original function. And instead of multiplying by the number in the power, we divide by it. So in words, what do you do when you integrate? You add 1 to the power and then divide by that new power. And at the bottom, I think I've written that, yeah, that asterisk. So this is the one we use most commonly, and in words it's worth remembering. How do I integrate? Add 1 to the power and divide by the new power. Okay? Let's look at these other examples and maybe put some examples in. So, for example, 3 sine 2x. The rule tells us the sine changes to a cosine. Any number that's inside comes out and goes underneath, and it becomes negative. So for this example, and you might want to put this in, the 3 stays in front. It becomes negative, because we note the negative sign there. We then divide by the number that's inside, which is the 2, and the sign changes to a cosine. The rest stays the same. So 2x plus c. So that would be an example of how this one's used. The next one, write down what you think the integral of this would be. So next example, 4 cos 2x becomes 4 over 2, which is 2 sine 2x plus c. E to the 2x, the a that's in front just comes out and goes underneath. The rest stays the same. So this becomes a half e to the 2x. 1 over x becomes log x. So if I have a number in front of it, like for example 4 over x, that's the same as 4 times 1 over x. This becomes 4 log x plus c. So, and then at the end, I think I've just put 1 or 2 very quick, or one very simple example. A constant, the x just comes in. So what's the integral of 4x plus c. So that's our table of integrals that we can refer to with some examples of how they work. As with differentiation, what we need to do now is just practice them. Okay?